Welcome and thank you for joining this webinar, The Architecture of Autonomy, Distributed Artificial Intelligence as a Native Capability of Future Wireless Networks, prepared by the Alpert Research Team. Wireless networks are entering an era where complexity, scale, and performance demands exceed what centralized control can manage. Distributed artificial intelligence enables networks to sense, learn, and act autonomously across devices, edges, and cores.
The report opens with this incredibly bold claim that we're moving away from the classical communication theories, and we're moving toward what the report calls native AI.
Why do we need to rethink something so fundamental?
Shannon's whole world was about the accurate reproduction of a message. You send bits, I receive bits, and the goal is to make sure what I get is exactly what you sent, despite all the noise in the channel. That was the game. But the Alpert report argues that in the 6G era, the goal isn't just communication anymore, it's action. It's about semantic understanding, it's about context, and it's about autonomous decision-making right at the edge.
So less about, did you get my message? And more about, do you understand what to do with my message?
The thing forcing this change is, well, it's scale and physics. You have to look at the numbers they cite. By the end of 2023, we already had about 29.3 billion connected devices online.
That's a number that's hard to even wrap your head around. And that curve is only getting steeper.
And the old model, the one we're used to, the centralized cloud model, where we just suck up all that data, piped it to a massive data center, is hitting a wall. It's starting to fail.
And how is it failing?
It's a mix of things. It's latency, it's the cost of bandwidth, and it's the actual speed of light. The report calls it the communication bottleneck.
Common assumption is just, well, we'll build more data centers. Bandwidth gets cheaper every year. Why can't we just keep scaling up what we already have?
You can, but you reach a point of diminishing returns, and it's happening faster than people think. The report gives this example using the Llama 2 model scaling. The goal was to train this massive AI model. They scaled the hardware from 8 GPUs all the way up to 1,024 GPUs.
You'd expect a massive speed up.
But what they found was that the model FLOP's utilization, which is basically a measure of how busy the chips actually are, it dropped from a decent 47% down to just 4%.
So you're telling me that 96% of the time, these incredibly expensive chips were just sitting there?
Exactly, just waiting for data, the communication overhead, just the time it takes to shuffle the data and the model parameters between all those chips. It ate up between 80 and 90% of the total execution time. In large-scale centralized systems, communication ends up dominating compute.
Right.
And that's a losing battle.
And when you apply that to a wireless network, with things like self-driving cars,
that's where it becomes a deal breaker. For anything that falls under URLC, ultra-reliable, low-latency communications, that latency is not just an inconvenience, it's a safety issue.
My car sees a pedestrian step into the road. It can't afford to send that video to a server 1,000 miles away, wait for an answer, and get it back.
The round trip, the physics of it, just takes too long. By the time the answer comes back, it's too late. So the report's argument is that we have to stop trying to force this square peg into a round hole.
The square peg being our centralized AI model.
And the round hole being the wireless network itself. Yeah. Wireless networks are distributed. You have towers, small cells, devices, sensors. They're all spread out.
But our intelligence has always been centralized in one place.
So the whole idea of DAI, or distributed artificial intelligence, is to align the intelligence with the actual topology of the network. If your network is distributed, your brain should be too.
So instead of fighting the network to bring the data to the AI, you bring the AI to the data.
And the performance gains they're seeing, well, they're not incremental. The report cites that early DAI systems are already achieving 21 to 35% cost reductions.
Which is great, but the performance?
They're seeing 2 to 15 times throughput improvements compared to the centralized models.
15 times. Okay, that is not a rounding error. That's a generational leap in capability. Where does a 35% saving actually come from?
It's mostly from avoiding backhaul costs. Just think about the sheer expense of leasing the fiber optic connection to haul terabytes of raw video.
You're paying for all that data transit.
But if you can process that video locally, right at the traffic intersection on an edge server, and you only send back the insight, a tiny packet of data, you've just cut your data transmission by, what, 99.9%?
We're shipping the answer, not the raw data.
And that's a direct operational expenditure saving. Why do we need to blow up the whole architecture and distribute the intelligence? Why can't we just build a bigger, faster server farm?
And it really comes down to 3 things: physics, privacy, and energy. Let's start with physics. The report calls it the cloud bottleneck.
And that's basically just the speed of light, right?
It's the speed of light, it's fast, but it's not infinite. The traditional model is a loop. A device sees something, it has to send that raw data, maybe a video feed, to the cloud. The cloud's AI processes it, decides apply brakes, and sends that command all the way back to the car. Now, if you're asking for the weather, a half-second delay doesn't matter. But imagine that self-driving car in a 6G network that needs to react to a safety hazard. We're talking about a class of service called URLLC, ultra-reliable, low-latency communication.
Define low latency in this context.
We're talking sub-millisecond, less than 1,000th of a second for the entire loop. If that data has to travel even a few hundred miles to a data center and back, you've already lost. Physics has beaten you. You simply cannot fight the speed of light. The intelligence has to be closer to the action. It has to be at the edge.
So physics is the first problem. It's a hard, non-negotiable limit. The report also makes a huge deal about privacy.
This is arguably even more important for the business case. Sending raw data everywhere creates massive regulatory liability. A group of hospitals want to pool their data to use AI to analyze patient x-rays. The old way is upload all those highly sensitive x-rays to a central server to train the AI.
Which means shipping incredibly sensitive patient data off premises across the internet.
From a compliance and security perspective, it's a nightmare. You have to anonymize it, you have to encrypt it, you have to pray the pipe is secure, and you're still creating this giant centralized honeypot of medical data that's a target for hackers.
So the distributed model flips that.
The report argues that in the DAI model, you don't move the data, you move the intelligence to the data.
The third driver you mentioned was inefficiency.
It's what the report calls the efficiency crisis. We are literally drowning in data.
From what?
Vibration logs from every motor, temperature readings from every valve, high-definition video feeds from every assembly line. And here's the thing, 99% of that data is just noise. It's just a constant stream of everything is normal. It costs a fortune. It costs backhaul bandwidth, those are the big fiber optic pipes connecting the cell towers to the core internet, and it costs electricity, both for transmission and for processing in the data center. It is incredibly wasteful to clog up the entire system with raw noise just to find that one tiny anomaly.
You want the local device to be smart enough to filter that out.
You want it to filter it out and only shout when there's a problem.
The report summarizes all of this as a complexity crisis.
It is a scale issue. Centralized control creates a single point of failure and a single massive bottleneck. The Alpert Research Team points out that managing billions of nodes, optimizing their spectrum usage in real time so they don't talk over each other, and keeping them all secure, it is just too much for one central algorithm to handle. It's like trying to run the entire economy of the United States from a single desk in Washington, D.C. It just doesn't work. You need decentralized decision-making.
So this is why the report is so emphatic that DAI can't just be an overlay technology anymore. It has to be a native capability of 6G baked right into the standard.
So the why is crystal clear. The old model is hitting the wall of physics and economics. Distributed artificial intelligence is central to the evolution of 5G Advanced and 6G, redefining how wireless networks are designed, operated, and trusted in the autonomous era.
It really is the future of the field.
And if you are interested in gaining a deeper understanding of the transformative power of wireless technology, the Alpert Research Team runs webinars where they explore these cutting-edge wireless innovations, their applications, and their implications. We encourage you to click the links below to learn more.
It's well worth your time if this topic is interesting to you.
Thanks for listening. We'll see you next time.